All right, hi folks. So we're back, and so we're thinking about Homework C2, question 2. In the first video, I kind of give you a background of frequency tests and the kind of the difference between the chi-squared test, which hopefully you've heard about in like IEE475, but if not, we'll get into in class, and the Kolmogorov-Smirnov test, which is or the KS test, which is most likely a new test for most of you, and that's what we're kind of practicing here. So. Let's go on and do the practice. So what I'm going to do here is I'm just going to generate a bunch of numbers, a bunch of random numbers. So this isn't something you do. I've given you the numbers on the homework, but I'm just going to generate them from an exponential distribution. I'm going to generate, let's say I'll generate 6 of them. So look at this. So we got 6, well, sorry. So I need, I'm going to regenerate them so that I can happen to get them all. That's good. So look at that. I've got 6 numbers, all in between 0 and 1. And if I didn't know that they were from an exponential distribution, somebody might claim that these were drawn from a uniform distribution, and I would want to test whether it seems like that could be possible using a Kolmogorov-Smirnov test. I can't use a chi-squared test because if I were to choose with only 6 numbers, there's kind of it's difficult for me to meet some of the conditions on the minimum number of expected counts per bins with only 6 numbers. And so the Kolmogorov-Smirnov test we use because we have so few of these, and we'll get into these details in class, but here I'm forcing you to use the KS test anyway, so it's not like you have a choice. All right, so we look at this and we take those 6 numbers. And I mentioned that effectively what we're going to do is we're going to sort those numbers. So I'm gonna take these 6 numbers and I will just manually sort them. Well, actually, here's what I'm going to do first. I'm going to create a little table inside inside Word. So I want to insert a table, and this table, since I've drawn 6 numbers, I want the table to actually have 8 columns. So I'm going to add a column on the left and the right, and I'm going to have it have 6 rows. So 8 columns and 6 rows. So 6 rows is good for any of these, and then 8 columns, that's just the number of data plus 2. All right, so insert that table. Okay. So I'm just going to label the second row of this table RI. And so RI, this here is the spot where we're going to put our 6 numbers that may or may not be uniformly distributed. But we need to put them in sorted order, because effectively what I'm going to do is in this column here, I'm going to basically say that this is the bin. If you remember from part 1 of the video, this is sort of the bin that corresponds to, if they were uniformly distributed, where would we roughly expect a first point to land if we sorted them all? And so the bottom of that bin will be 0, and the top will be, well, I have 6 numbers, so it'll be 1 over 6. So 1 over 6 is basically 1 point, or 0.167, 1.667. So that's, I guess, the downside of me using 6 is I've got this round off error that I have to worry about. So these are the boundaries of that first column. And if I look at the numbers that I drew here, so I'm just looking at these 6 numbers, I look for the smallest number, which to me looks like 0.127. So I'm going to put that here, 0.127. And then I want to ask, so my second bin, if I have 6 numbers, my second bin goes from 0.16667 to basically 0.3233, so a third. So, and then my second number, if I look in this list, it looks like the next biggest number is 0.3381. All right. So basically the pattern is going to go that across the top here, I'm going to keep increasing by a 1/6. And I choose 1 over 6 because I have 6 numbers. If I had 8 numbers, I would increase by 1 over 8. If I had 4 numbers, I'd increase by 1 over 4. So, of course, so then this next one is going to be 0.5 because that's 3 over 6. And then this will be 4 over 6, which is 0.66667. And this next one, 1, 2, 3, 4, is going to be 5 over 6, which is 0.833333. And then if we did everything right, this last one should be 6 over 6, or 1.0. And then basically this same pattern across the top is followed across the bottom. So again, the way you can think of this is that this is the lower side of the expected bin that the first number should fall in. This is the upper side of the expected bin that the first number should fall in. This is the lower of the second bin, upper of the second bin, lower of the third bin, upper of the third bin, lower of the fourth bin, upper of the fourth bin, and so on. So each one of these are like these little bins, and then then we just rank the drawn data here in order. So 0.127 was the lowest, 0.3338 was the next biggest. If I look at the data, it looks like 0.360 comes after that. After that, then I get, looks like 4028. After that, I get 4152. And then my last number is 5915. All right, now just looking at this, I noticed that there's something suspicious here, that if these were uniformly distributed, I would expect the highest number to be pretty close to this bin, between 0.8333 and 1, and it's way lower than the bin. Likewise, I would expect the next lowest number to be 0.666 to 0.8333, and it's way lower than the bin. So already I'm getting the feeling that these probably aren't uniformly distributed, but the KS test allows us to then sort of actually rigorously test for that statistically. All right, so I'm just going to label this column I over n, and this column I minus 1 over n. So to sort of see where I get those numbers, if I were to sort of space, let me see if I can shift this table down. So if I were to go outside this table, let me see here, just cut the table, paste it back here. So since I have 6 numbers, and so n is equal to 6, and then so if you can think of, I guess if I wanted to, I could go up to table and I could insert a row above this, and I could call this I, and then you could say this is 1, 2, 3, 4, 5, and 6. So you can think of this Ri, like R1 is the lowest in the rank, R2 is the next lowest, and so on when they're ranked by their value here. So so this one here is just 1 divided by n, that's this, 2 divided by n, 3 divided by n, 4 divided by n, 5 divided by n, 6 divided by n. And likewise, this is 0 divided by n, 1 divided by n, 2 divided by n, 3 divided by n, 4 divided by n, and 5 divided by n. So that's where we get those. Now, what do we put in these next 2 rows? Well, this one is I over n minus Ri, and this one's going to be Ri minus I minus 1 over n. So I'll make this column a little bigger to accommodate. All right, so as you can see, what this cell is going to be is the difference between Ri and the top of the bin, and this cell is going to be the difference between Ri and the bottom of the bin. So if I look here, I'd say, well, I'll just go over to MATLAB so we all can see this math. And I can see that 0.16667 minus 0.127 is 0.0397, so I'm going to put that in there. And then this Ri minus that, well, that's just 0.127 minus 0, so I'll just, I mean, it's obviously going to be 0.127, but I'm just going to put it here so we all can see the calculations. So I can put 0.127 down in there. And so then the next one here, I do the same sort of thing, 333 minus 338. Well, I know that this number minus this number is going to be negative, so I don't even need to calculate that. So I'm just going to put a little dash there. So I'll put that symbol there. And then down here, 0.3338 minus 0.1667, well, I can do that over here. So basically, if you didn't catch that, If any of these calculations come out negative, so if this one minus this one is negative, or if this one minus this one is negative, well, don't even bother with it, because we're looking, in the end, we're looking for the greatest positive number. So if they're going to come out negative, we don't care about them anyway. So I can just, not even do that calculation. So here, 3381 minus 0.1667, so I'll go over here and do that. 0.3381 minus 0.16667, and I get 0.1714. All right, so go over here, 0.5 minus 0.36, 0.5 minus 0.36, and that's 0.14. 0.36 minus 0.3333, 0.267. We're almost done. So then again, you can imagine if you did this in a spreadsheet, then all this math could be done for you. I'm just kind of doing it all by hand so everybody sees what's going on. 0.4028 minus 0. Okay, so here's an example. I don't even have to do this math, because 0.4028 minus 0.5 is going to give me a negative. So I'm just going to fill that. Now here I can see that this one is also going to be a negative, and this one is also going to be a negative, but these will be positive. So I can look up 0.83333 minus 0.4152, and I get 4181, and then 1.0 minus 0.5915 gives me 4085. All right, great. So we're almost done here. So, so then I'm just going to put a little max here to tell me that what I'm going to put down here is the maximum value of this row. So if I look across here, looks to me like it's 0.4181. And then if I look across this, the maximum value of this row looks like it's 0.267. Now, I'm actually going to name these like we do in the book. So we call this D plus, and we call this D minus. I recommend you do something similar, because the TA is probably going to, the grader is probably going to be looking for that. And then I look across both of those, and then I finally get my test statistic, which is just the maximum of these two maximums, 0.4181. So effectively, I've looked at all of these are my sorted numbers here, and I've assigned them each to the bin that if they were uniformly distributed, that's the bin they should be closest to, because uniformly distributed numbers should sort of show up equally across the number line. So when you sort them, then they all should kind of be close to this bin that's of width of 1 over n, where n is the number of numbers. And so I calculated their maximum distance from their position to the edge of their assigned bin. And then I took the maximum of all those distances, and I found out the maximum distance is 4181. That is my test statistic for the KS test. So my question is now, is this, based on that test statistic, does that imply that these numbers are significantly different from a uniform distribution? Well, how do I test that? Well, I look in the back of the book, and I've happened to have a reproduction of that. Let me bring that up. So if you look on page 601 of your textbook, you'll find table A8. Table A8 has the Kolmogorov-Smirnov critical values. And they have this column degrees of freedom, and then they have these two columns, D.1, D.05, and D.01. Now in this problem, I've set the alpha equal to 0.05, as I usually will. So this is your sort of type 1 error rate. And so we'll talk a lot more about what that means in class if you don't remember. But basically that is represents, if we how often we're going to find a uniformly distributed random variable that's going to generate numbers that we're going to reject by this test. So and that, so we say that we're going to limit that to 5% of the time. When we know that it actually is uniform, how often are we going to falsely reject it? Well, 5% of the time. So that's what our type 1 error rate. But the important thing for the mechanics of getting this test done is that 0.05 tells me that I need to look at the middle column here, because that's what that D.05 is. These are the critical values for an alpha of 0.05. So then I say, well, then what are my degrees of freedom? Now, again, we'll go over this in class a little bit more, but basically the degrees of freedom are how many dimensions can your data vary away from the null hypothesis. And so for a KS test, because we haven't estimated any parameters of the distribution we're testing against, then the degrees of freedom are actually just the number of data. So for other types of tests where you actually estimate parameters, you sort of force your hypothetical distribution to be closer to the data than it would be if you didn't estimate the parameters. And that's why the degrees of freedom, you've probably seen tests where your degrees of freedom are not the number of data, they might be the number of data minus 1. Or they might not be the number of bins, they might be the number of bins minus 1. So like in a chi-squared test, you might have seen that the degrees of freedom is the number of bins minus 1 because the first 3 bins kind of determine how big the 4th bin is, because you only have so many data points. So when you add up the first 3 bins, the 4th bin is kind of stuck at whatever value it's supposed to be. And so you only have 3 degrees of freedom when you use 4 bins in a chi-squared test. But in a KS test, we didn't do any of that. We have 6 ways in which the data can vary away from a hypothetical distribution. So our degrees of freedom are 6, are just the number of data. So I look in the middle column where the degrees of freedom is 6, and I find that my critical value is 0.521. So I'm just going to make I could say D star or whatever, my critical value is 0.521. And so the question is my test statistic greater than my critical value? And in this case, no. The test statistic is not. So my test statistic is less than my critical value. And so in that case, we cannot reject the hypothesis that these data are uniformly distributed, or that these data come from a uniformly distributed random variable on 0 to 1. And you might think that's funny, because I know if I look up here, these were generated from an exponential. But what this is telling me is that if I look back at the table here, notice that as I get more and more data, my threshold gets smaller and smaller. Okay, so what this is sort of saying here is that when you have only 6 bins, then the bins are naturally pretty big, right? I mean, the width of a bin is 0.1666. So already, even if you were inside the bin, you could be inside the bin and be 0.1666 away from the top edge of the bin, and so already, that's not so great. So if I only had 1 data point, then regardless of then I'm going to have a very high numbers. And so like up here, the critical value for if I only had 1 data point, the critical values here are like 0.975. So that would mean that I can tolerate being 0.975 away from the bin. That means that I can really, I could be, if the data landed right at 0, then I would reject the hypothesis. But if you were slightly higher than 0, you would be less than 0.975 from either barrier, and you couldn't reject. So this does not mean that these data are uniformly distributed. This just means that either they're not uniformly distributed, or we don't have enough data to be able to detect the difference between them and a uniformly distributed random variable. So it's like the effect is, we don't have enough data to detect an effect of this small. So there is an effect. So there is a test statistic here. This 0.4181 this is sort of like an effect that, this is detecting a difference from what you might expect. But with so little data, then this difference is not big enough for us to detect it. Now, if this difference would have happened to be above point, if it was 0.6, then we would reject the hypothesis conclusively. We'd say, no, these data to a 5% certainty level, significance level, are not uniformly distributed. So I'm just I'm belaboring the point here that even though we know the data came from an exponential distribution, we still cannot reject that they might be uniformly distributed. And if you kind of look at it, it actually sort of makes sense, because really things only start looking really ugly up here for these two data points. So for this data point, like this point is right in the middle of the bin. This point is basically right in the middle of the bin. This point is basically right in the middle of the bin. These are all inside the bins that they were expected in. So I'm okay. So I said this one's basically right in the middle of the bin. This one's slightly over the bin, but it's not very far out of the bin. And then we get to this one, and it's a little below the bin, but it's only a little below the bin. So things get uglier for these two, but they don't continue to get ugly. Like this one actually is less ugly than this one. So with only 6 data points, it's just hard to tell. So we cannot reject that hypothesis. All right, so let's do a second example where we actually use data that did come from a uniformly distributed random variable, and see what happens there. So you get to see this process all over again, but I'll do it with, say, 7 numbers this time. So I'm going to call for randomly distributed so these are 7 numbers, uniformly distributed between 0 and 1, and I got 7 of them. So what I can do is I can reuse this table. So what I will do is I'm just going to go up to table, and I will insert a column to the right, and I'm just going to label this 7. And so I can then now get rid of all of the data in the table. So I just want to clear those cells. And I will also, just so we don't accidentally carry that down. All right, now that you've seen how we set the critical value, I may as well update this right now. So I know ahead of time, without even putting in my data, what my critical value is going to be. So if I go over to the preview, I can say, all right, I'm interested in 0.05, this middle column, with 7 data points, and it looks like 486 is my critical value. So I'm just going to change that right now. And I don't know what my conclusion is, so I'll get rid of that right now. And when you guys do this on your homework, I want you to make it a little cleaner than this. I'm just trying to demonstrate how to populate this table. And I'm doing it inside Word because that's easier to sort of screen record. And then maybe, you guys can, if you want to, you can feel free to do it this way rather than writing it down on paper and then having to translate it back into Word, because we do want these tables to be kind of digitized. It makes it easier for the grader, and again, it's good practice. All right, so I got my critical value set. All right, so now I just need to sort these. So I need to pick, what I can do is I can say, all right, well, what's 1/7? 1/7 is 0.1429. Oh, well, so 7 is kind of an ugly number for me to use here. But I can keep track. So I'm going to just put these across here. So I know that this I want to be 1/7, 1429, 2857, 4286, 5714, 7143, 8571 1.0. And then down here I know this one's 0, and then I just take these up to the 6th one and I can paste them in down here. And I got my bins. Good. So now I look back at my randomly distributed numbers. I look, well, what is the lowest number? 0.3786. It's really the lowest number here. So even though I drew these randomly, 0 to 1, that's pretty ugly, right? You know, like for 7 numbers, if these are truly uniformly distributed between 0 and 1, we expect that first number to be close to this bin. And off the bat, the lowest number in this sequence is not in that bin. So this is another good example of you know, how things can work. All right, so what's the next number? Looks to me like 5108. After that, 5328. After that, 5108, 5328, 6443. And then 7948, and then 8116, and then the last number 8176. I'll just make that bold to match the others. So this first one I don't have to do because it's going to come out negative. The second one is 3786. This one's also going to come out negative. But then this one, 0.5108 minus 0.1429 is 0.3679. Now this one here is going to come out negative. Actually, I'm just going to go through. This one here is going to come out negative. This one here is going to come out negative. This one will not, and so those will be okay. And then now I'm looking at this difference. So that's 0.5328 minus 0.2857, 2471. Now I look at 6443 minus 0.4286, 2157. Then I look at 7948 minus 5714, and that gives me 2234. Then I look at, now I can calculate this one because it'll be positive again. 8571 minus 0.8116, 0455, and then 8116 minus 0.7143, 0973, 0973, and then this one will be negative, so don't worry about that. But then this one, that's 1 minus 0.8176, 0.1824. All right, now I look across here. What's the maximum of this row? 1824. Look across here. What's the maximum of this row? 3736. Looks like 3786. What's the maximum between these two? All right, this is my critical value that, again, if you're coming in late, if I look back at my preview, I've got 7 numbers. So I look in the row 7 here for the KS test, and I got a significance level 0.05, so D 0.05, and my critical value is 0.486. And so this is my test statistic here, and this is my critical value. And so is my test statistic greater than the critical value? No. Just like before, then we cannot reject the hypothesis that these numbers are drawn from a uniformly distributed random variable between 0 and 1. All right, so so in both cases we got the same conclusion, no, and that even though one was drawn from a uniformly distributed random variable and the other one wasn't. So this one we actually were kind of hoping that this would be the right result, because we don't want to reject MATLAB's pseudo-random number generator because it's hopefully a good pseudo-random number generator. But we would want to reject the exponential, but we couldn't reject the exponential, and it's my claim that if we got more data out of the exponential, then we probably could reject the exponential. So, I mean, as an example, an exponentially distributed random variable will give you numbers greater than 1. Well, those will be way off the charts in terms of these distances here. So if I were to redo that, eventually I would get a number that was way larger than it's been, and then it would almost definitely be rejected. But it was just bad luck. And it was kind of because, remember, I drew the random numbers from the exponential initially, and it was, and I did get one that was greater than 1, and I said, I don't want to do that. So I redrew, and so I kind of did a little bit of what we call p-hacking here, that I end up biasing my results by randomly drawing again until I got one where all the numbers were between 0 and 1. But still, I claim that if I would have drawn, 50 numbers and they all happen to be between 0 and 1, they would all most likely be clustered closer to 0 because it's an exponential than they would to 1, and so it would probably end up rejecting it. All right, so if we look back at what the homework asks, I've got the homework up here on another screen, and so I think I asked you to do a little bit of interpretation. So I said, comment on whether you can infer from this result that the PRNG is a good approximation of a uniform random variable. Now, in both of these cases, you actually, your inference is very limited. We know that this one at least cannot be rejected, so there's no evidence that this is a bad random number generator in both cases. If one would have come up rejected, then we could say for sure that at least to our significance level, this is not; those would not be good random number generators. But when they both come up insignificant, so when they both come up less than the critical value, then the best we can say is that there's no evidence to say that they're a bad random number generator for these number of data. But we would need to do more intensive study in order to really understand whether we had enough statistical power, a term we'll introduce later, to really understand whether whether we can trust that this result means that they're good random number generators or just simply random number generators that generated too little data for us to tell the difference. I hope that makes sense. But anyways, I hope that that ends up helping you figure out how to fill out these tables. If you need more help from that, if you read the homework carefully, I've told you where else to look in the book for other examples of the KS test. You also can look at the lecture slides as they come out when we cover this content in class. So I guess that's it.